Thank you for standing by. At this time, all parties are in listen-only mode until the question-answer session of today's conference. To ask a question at that time, please press star one, unmute your phone, and record your name. I'd also like to inform all parties that today's conference is being recorded. If you disagree, you may disconnect at this time. It is now my pleasure to turn the call over to Ms. Alana Johnson. Thank you, and you may begin.
Thank you. Hi, I'm Alana Johnson, Public Affairs Officer at NASA headquarters in Washington, D.C. Welcome to today's media teleconference to discuss asteroid science and planetary defense. For those watching via live stream at nasa.gov/live, please note there will be a 30-second delay in the streaming to the actual telecon. Today we have 5 panelists joining us. Each panelist will provide brief remarks, and then we will move to question and answer, accepting questions from media who are dialed into the phone bridge and those who are submitting questions via Twitter using the hashtag AskNASA. This media telecon will be limited to 1 hour. Asteroids have been orbiting the sun for thousands of millennia in deep space, standing as ancient storytellers, holding clues about the formation of the solar system. NASA's first mission to collect a sample from an asteroid, the origins, spectral interpretation, resource identification, security, Regulus Explorer, or OSIRIS-REx, is now ready to make its first attempt of collecting a sample from the surface of a potentially dangerous asteroid Bennu and bring its secrets home to Earth. But NASA has several other asteroid missions coming up with varying purposes, as well as a very dynamic program to help us identify and learn more about potential hazards and defend our planet. Today's 5 panelists are Lori Glaze, Planetary Science Division Director at headquarters in Washington; Hal Levison, our Lucy Mission Principal Investigator from the Southwest Research Institute in Boulder, Colorado; Lindy Elkins-Tanton, our Psyche Mission Principal Investigator at Arizona State University in Tempe, Arizona; Andrea Riley, our DART Mission Program Executive at NASA headquarters in Washington; and Jamie Elsala, Research Scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. And with that, we'll get started. I'll hand it over to Lori to kick us off.
Thank you so much, Alana. And of course, we are all really, really excited about the big event that's going to happen tomorrow for OSIRIS-REx, where we're actually going to take a sample of asteroid Bennu. But as Alana said, we have lots of interest in asteroids across the solar system. And the reason is that asteroids are these rocky remnants left over from the early formation of our solar system, approximately 4.6 billion years ago. And while the planets and moons have changed over the millennia, many of these small bodies of ice and rock and metal haven't. So the asteroids are like time capsules floating in space that can provide a fossil record of the birth of our solar system. We're really interested in exploring the diverse population of these small bodies that are sometimes classified by where they're found in the solar system, because they can provide valuable information about how the planets, including our own, came to be. The small worlds could also help answer questions about astrobiology, which is the study of the origin, evolution, and distribution of life beyond Earth. Most of the known asteroids are found orbiting the sun between Mars and Jupiter within the main asteroid belt. And some of these are highly unusual, like 16 Psyche, which appears to be a world not primarily of rock and ice, but mainly of metal. And there's a photo of that, an image in the bottom center of the graphic that you can see. Other asteroids that lead and trail Jupiter in its orbit are called the Trojans, and you can see these in the lower left graphic. These are clustered into 2 groups due to the balanced gravitational pull from both the Sun and Jupiter, and are thought to be remnants of the primordial material that formed the outer planets. And while asteroids can provide a treasure trove of knowledge for planetary scientists, some may also one day pose an impact threat to Earth. But thankfully, there are no asteroids that we know of that are impact threats to Earth over the next 100 years. But NASA has established the Planetary Defense Coordination Office in 2016 to manage NASA's ongoing efforts in planetary defense to find, track, and monitor any near-Earth objects or asteroids and comets that come within 30 million miles of Earth's orbit. Bennu, the destination for OSIRIS-REx, is a near-Earth object with a 1 in 2,700 chance of impacting Earth at the end of the next century. And OSIRIS-REx has provided really important information to help us refine our estimates of when Bennu may come close to Earth in the late 2100s. Now, I'd like to turn it over to some of the scientists and engineers who are part of NASA's mission studying the various asteroids across our solar system. I'm looking forward to hearing more about the exciting work that they're doing with these missions and why they're so important for NASA and planetary science. And so with that, I'm going to toss it over to Hal Levison, the principal investigator for the Lucy mission.
Thank you, Lori. So my name's Hal Levison. I'm from the Southwest Research Institute in Boulder, Colorado. I'm the principal investigator of Lucy, which is the first reconnaissance of the Trojan asteroids. As Lori did a great job of explaining, these asteroids lead or trail Jupiter in its orbit by about 60 degrees. The way to think about it is that if you put an object exactly 60 degrees in front of Jupiter, the gravitational attraction of the Sun and Jupiter plus the centrifugal force of rotation means that the object will stay there forever. So the objects that we see in these orbits are objects that are primordial and left over, particularly from when the orbits of the planets were set in place. So Lucy is going to launch in 2021, a little less than a year from now. October 16th of next year is when our launch window opens. It's amazing to think it's less than a year away. We're going to rattle around the inner solar system for a couple of years using Earth gravity assists to scatter the spacecraft more distant orbits from the Sun. So we're going to have 2 gravity assists initially. We're going to launch into a 1-year orbit, have a gravity assist into a 2-year orbit, and then have a second gravity assist that's going to kick us out into the Trojan swarms. On the way out, we're going to encounter a main belt asteroid named for Donald Johanson, who was the discoverer of the Lucy fossil. I should say, again, Lori did an excellent job of explaining how these objects are really the fossils of planet formation. So we named Lucy the spacecraft after the Lucy, the fossil, in order to honor that. Then we get out into the leading, or what we call the L4 swarm, and we're going to have encounters with 4 objects there. We're going to have 4 encounters there, right, for a total of 5 objects, because one of our objects was recently discovered to have a neat little satellite. Then we're going to come around into the inner part of the solar system again, have another Earth gravity assist, which is going to take us to our 6th and 7th Trojan, which is a near equal mass binary called Patroclus. As Lori said, these are incredibly important objects from the point of view of understanding planet formation. Of those of you who don't know my history, I'm actually a theorist who has spent a career trying to understand what the small body populations are telling us about how the planets formed and evolved. And these objects are relatively pristine from that time, and yet they were highly affected by planet formation themselves. So by studying these objects, we will get an excellent understanding and more constraints on how the planets formed and evolved. One of the interesting things about these objects, which were not understood initially before we started studying them with telescopes, is that the Trojans, despite the fact that they're in a very narrow region of space, are very different from one another. They have different colors, different spectra, and that probably means that they formed in very different regions of the solar system and were actually delivered to the orbits we see them today as the planets grew and evolved. So this diversity is telling us something important about the planet formation process, But in order to understand what that the message they're trying to send us is we have to understand that diversity, and that's why Lucy is designed to travel to so many of these objects. So if you look at our objects, and I said there are 7 Trojans that we're visiting, they cover all the range of colors and spectral types, and also a wide range of sizes, from objects that are 100 kilometers across to this new little satellite called Keta, which is about 1 kilometer across. And so that's going to tell us about the chemical variations and also the collisional evolution, which of course led to the planets that these objects studied. But in addition to this diversity, actually, some of the objects we're going by are interesting targets for spacecraft in and of themselves. And there's 2 systems that I want to talk about. The first is the first encounter we're going to have with Trojans, which is going to be in 2027. And that's with the object Euripides, which I already said has the satellite called Keta. It is the largest member of the only major disruptive collisional family in the Trojan swarms. And what that means is that although space is big and these objects are very far from one another, matter of fact, if you stood on one of the Trojans and looked out at the sky, you wouldn't be able to really see any other Trojans. They are fairly well separated, but every once in a while there's a collision. And if the collision is big enough, the target of that collision will break apart, forming a swarm of smaller objects, fragments, that are in similar orbits about the sun. So we can identify these families by looking for clumps in the orbits, and Euripides is one of those clumps. So by studying Euripides, we're going to understand how collisional processes occur. The other one, which is sort of another extreme, is the Patroclus-Menetius binary, which is the last guy we're going to encounter. As a matter of fact, it's my favorite. It's a near equal mass binary. So these are 2 objects about 100 kilometers in diameter that are on circular orbits around each other with a separation of about 700 kilometers. These are very rare. These types of systems are very rare in the inner part of the solar system. And for this context, what I mean by inner part of the solar system is basically inside the orbit of Neptune where the planets are. But if you look out into the Kuiper Belt, into regions that were not highly affected by the planet formation process, they're all over the place. Over half objects that we see are these near equal mass binaries. And so what theorists have come to the conclusion, and they're actually theories that produce these kind of systems, is the first real macroscopic objects in the solar system were probably these equal mass binaries. And they're very rare in the inner part of the solar system, right? Because planet formation is so violent that the binaries were torn apart. If all that is true, then the PM binary is one of the pristine primordial objects that just happened to escape the violence of planet formation. So it's going to be very interesting to see. So, as I said, Lucy's going to launch in 2021. We're going to have our first Trojan encounter in 2027. Our last in 2033, on March 2nd, which is the day after my 74th birthday. And we're carrying on the mission 3 scientific instruments. One is a high-resolution panchromatic camera that's called LORI, that it traces its heritage to the instrument aboard New Horizons. So if you remember seeing the beautiful images that New Horizons produced, we're going to produce something similar with this instrument. We have an instrument that's called LaRalph, which is actually 2 instruments in one. It's a color camera and a near-infrared imaging spectrograph. So we're going to get near-infrared spectra of these things, looking at compositions. That also traces its heritage to an instrument that's now aboard New Horizons. And what we call LATES, which is a thermal infrared spectrograph, which is going to help us measure the temperature of the surface of these objects, giving us some idea of what the structure of the surface is. And that is actually a clone of an instrument that's aboard OSIRIS-REx right now. So I just want to end by putting Lucy in context. In the whole history of the unmanned exploration of small bodies, we've visited 8 main belt asteroids. Now, main belt asteroids are more akin to terrestrial planets than they are to the giant planets. But we have learned so much from those 8 encounters that it basically has revolutionized our understanding of the asteroid belt and the formation of terrestrial planets. Lucy, in one mission, will visit almost as many objects, 7 in the Trojan swarms, which are linked more to the outer solar system, as has been done in the entire history of the main belt exploration so far. And we expect we will revolutionize our understanding of the outer planets, just like those 8 missions revolutionized our understanding of the main belt asteroids. So I'll stop there. Thank you.
All right. Lindy Elkins-Stanton here, Principal Investigation of the Psyche mission. Hello, everyone. Psyche is both the name of an asteroid in the main belt, orbiting out past Mars, and it's also the name of our mission to visit that asteroid. The asteroid Psyche is large for the main belt. It's about 225 kilometers in diameter. I'd like to say it's about the size of the state of Massachusetts, where I've spent a lot of my adult life. It holds on all on its own. It holds about 1% of the mass of the entire asteroid belt, and it has mysteries. Its density and its radar and its reflected light properties indicate that it's largely made of metal. There are only about 9 asteroids out there of the almost 2 million asteroids known in the main belt that we think are metallic. And Psyche is by far the largest and also the roundest of them. So it's an entirely unique object in our entire solar system. Now, people have visited or sent robots to visit worlds made of rock like the moon and Mars, or of ice or gas like Jupiter and Titan and Europa, and in fact, the Trojan asteroids that we're going to see soon. But we've never visited a world made of metal. So if Psyche does turn out to be what we think, we'll be visiting a new kind of world, a kind of world we've never photographed or studied. Our spacecraft will launch in August of 2022, just 21 months away. And although 21 months might seem like a long time, we have every moment scheduled between now and then to make it to this launch. And the spacecraft will begin orbiting Psyche in 2026 after transiting through space for over 3 years. We will orbit the Psyche asteroid for almost 2 years, learning as much as we possibly can about this enigmatic asteroid. We'll determine whether Psyche is part of the metal core of a broken, tiny planet from the earliest times in our solar system. This is our best idea of what Psyche might be. We'll also look at its craters to learn about the age of its surface and at its composition to see if it's made of the same material we think Earth's distant and unreachable metal core is. And we'll study the topography of this metallic world to see if craters look the same as they do in rock or in ice, and see what kind of features it might have. But one thing I can promise you for sure is that when we arrive, we will be surprised. The astonishing things that we find off our planet always outstep even our best imagination of what to expect. Psyche will surprise us, and our whole Psyche team looks forward to sharing all that we discover with everyone here on Earth. Thanks.
Thank you so much, Lindy. We'll go on to our next panelist. Okay. Hi, everyone. My name is Andrea Riley, and I'm the program executive for the Double Asteroid Redirection Test, or DART mission at NASA. So in 2016, NASA established the Planetary Defense Coordination Office at NASA headquarters to manage NASA's ongoing planetary defense efforts and to coordinate within both the U.S. interagency and international efforts. So these types of efforts include discovering and tracking asteroids and comets that enter Earth's vicinity, characterizing their physical properties, so learning things like the size, mass, structure, composition, and mitigating, if needed, any that may pose a threat to Earth, and also continually assessing the hazard of a potential asteroid impact with Earth. So for an effective planetary defense, you must find any potential asteroid impactor with as much warning as possible. NASA-funded ground-based telescopes survey the sky every night to find and track near-Earth asteroids, which are asteroids that come within 30 million miles of Earth's orbit. Additionally, NASA is developing the Near-Earth Object Surveillance Mission, which will be a specialized space telescope to accelerate the discovery of the entire potentially hazardous object population. Mitigation of a potential asteroid impact threat is an important part of NASA's planetary defense planning. Should an asteroid be discovered that poses a future threat, we want to have a demonstrated mitigation capability. This is why the DART mission is important. DART is NASA's first planetary defense demonstration mission. It is directed by NASA to the Johns Hopkins University Applied Physics Laboratory, also known as APL. DART will demonstrate the kinetic impactor technique to test one method of asteroid deflection, and it will be the first demonstration to change the motion of an asteroid in space. DART will target the binary near-Earth asteroid system Didymos, which consists of two asteroids. A larger asteroid called Didymos, which is about a half-mile across in size, and a smaller moonlet asteroid called Dimorphos, which is about 535 feet across in size. So the system, the smaller asteroid Dimorphos, orbits the larger asteroid Didymos. DART will impact the smaller asteroid with the goal of changing its orbital period around the larger asteroid, Didymos. The Didymos system is the ideal candidate for DART, both because it poses no actual impact threat to Earth and because we can measure the time it takes the smaller moonlet asteroid to orbit the larger asteroid with ground-based telescopes, both before and after, to measure DART's impact when the system is about 7 million miles from Earth. Riding along with DART is the light Italian CubeSat for imaging asteroids, or Lucia CubeSat, provided by the Italian Space Agency. Lucia Cube will separate shortly before DART's impact with Dimorphos and image DART's impact in ejecta, giving scientists an additional view of the kinetic impact event. The European Space Agency's Hera mission will travel to the Didymos system a few years after DART's impact to fully characterize the impact site. All of this information will help planetary defense researchers validate computer models used to simulate asteroid impact and deflection techniques. So DART is scheduled to launch next July 2021, and will impact Dimorphos about 14 months later in the fall of 2022. And it will launch on a Falcon 9 rocket from the Vandenberg Air Force Base. And so now I'd like to turn it over to Jamie.
Thanks. So I'm Jamie Elsola. I'm a research scientist in the Astrobiology Analytical Lab at NASA Goddard Space Flight Center, and I'm a collaborator on the science team for the OSIRIS-REx mission. And my lab focuses on analyzing extraterrestrial materials like meteorites and moon rocks to look for the building blocks of life and to understand the origin of life on Earth and potentially elsewhere. And it's for that reason that I'm really excited to talk today about asteroid Bennu, which is the target of the OSIRIS-REx mission, and explain why we're so excited about the sample that will be returned from Bennu by OSIRIS-REx in 2023, and how it's going to help us answer some important astrobiology questions. So Bennu is a primitive carbonaceous asteroid that records the earliest history of our solar system. And carbonaceous means that it's relatively rich in carbon, so that makes it unlike Psyche that we heard about earlier. And the fact that it's carbonaceous means it has the potential to contain organic molecules like those that make up life on Earth. Organic molecules are made of chains of carbon bonded with atoms of oxygen, hydrogen, and other elements, and these molecules make up all living things on Earth. Some examples include amino acids that make up proteins, or nucleobases that are the building blocks of DNA. So we know from observations of Bennu that it's similar to a class of meteorites called carbonaceous chondrites. And carbonaceous chondrites have been studied on Earth and are known to contain high carbon abundance and a rich suite of these organic building blocks. And there's a recent paper that came out from the OSIRIS-REx team that shows evidence for widespread carbon-bearing organic material on the surface of Bennu. So we have really good reason to believe that the Bennu sample, when it returns, is going to contain a lot of these organic molecules, these building blocks. The O in the OSIRIS-REx mission stands for origins, and that's because one of the prime goals of the mission is to understand the origins of the solar system, and that includes the origin of life on Earth. So from an astrobiology point of view, studying Bennu is going to help us better understand the role that asteroids might have played in delivering these life-forming compounds to Earth. It's really important to note, though, that we're not looking for life or evidence of life on Bennu. The asteroid's much too small. The radiation environment would kill anything living on it. We do not think there is life on Bennu. But we're looking for those building block molecules because those are going to help us understand what the ingredients were in the early solar system when life arose on Earth and how those organic molecules might have been delivered to the Earth's surface and maybe to elsewhere in the solar system as well. So how are we going to do this? Well, the sample is going to arrive back on Earth in 2023, and the science team will be able to use cutting-edge instrumentation and techniques to test hypotheses. And these hypotheses include questions about the presence and identity of organic molecules that are used in terrestrial biology and whether those molecules are found in the Bennu sample. Bringing the sample back to Earth means we can use much better equipment than we're able to send to space. The instruments in my lab, for example, are much too big and use too much power, and they weigh too much to be able to send into space to do these measurements at the asteroid. So because OSIRIS-REx is collecting a sample and bringing it back, we're going to be able to use these cutting-edge instruments to be able to really analyze the sample. We're also going to be able to apply the context from OSIRIS-REx's observations of the asteroid. OSIRIS-REx has many global observations and has studied Bennu while it's been in orbit there, and we'll have all of that context information to apply to the sample analyses that are done in labs on Earth. One thing that I'm particularly excited about is that the Bennu sample is being collected really cleanly, and that's in contrast to what happens when a meteorite from an asteroid lands on Earth. As soon as a meteorite lands on Earth, it's exposed to the terrestrial environment, and we know that there's life everywhere on Earth, and that means that these building blocks of life are everywhere on Earth. And that can make it difficult to pick out exactly which organic molecules were present in the meteorite and what is terrestrial contamination. But in contrast, the OSIRIS-REx mission has put great efforts into minimizing, controlling, and understanding any potential terrestrial contribution or contamination to the sample. So we're really going to be able to study this carbonaceous sample. It's going to be pristine, and we're going to be able to understand those organic building blocks that might be present. And although the science team is really looking forward to digging into the sample as soon as it gets back, it's also important to note that the mission is going to archive 75% of the returned material. And that's going to allow people not yet born, using techniques not yet invented, to answer questions not yet asked. The Bennu sample is going to provide important science information now and also for generations to come. And so we're really looking forward to searching for these organic molecules to help us answer astrobiology questions, and also to compare Bennu to other small bodies and other asteroids within the solar system. And so the Japanese Space Agency's mission, Hayabusa 2, which is bringing back samples of asteroid Ryugu, will be a nice comparison. And then also comparing Bennu to the other small bodies, including the ones we've heard about today, such as Psyche and the Trojans, are really going to help us to understand the diversity of small bodies within the solar system. So I will stop there.
Thank you so much, Jamie. Lori, we'll roll into the question and answer session here now. We have several reporters on the telephone bridge today. We'll need to limit everyone to one question and one follow-up, and if there's time permitting, we'll follow back through that cycle. Today, our operator will identify you, but if not, please do identify yourself and your media affiliation, and then direct your question to a specific panelist if possible. For those dialing in, please push the *1 keys on your phone to be placed in the queue. And for Twitter, in addition to Ask NASA, please also submit your questions to #to Bennu and back. Sandy, let's go ahead and open the lines for questions.
Thank you. And as Alana had said, please to ask a question over the phone, please press *1, ensure your phone is unmuted, and record your name to ask the question. To withdraw that request, press *2. One moment while we wait for any questions to come in. Our first question comes from Marcia Dunn. You may go ahead.
Yes, hi. This question might be for Dr. Glaze. I'm wondering if NASA has any other missions in the pipeline to actually bring samples back from an asteroid, and whether yes or no, how much harder is it to actually, I mean, these all sound like really fabulous missions, and I'm sure they're all difficult in their own way, but how much harder is it to actually bring something back from an asteroid? Thanks a lot.
It's a great question, Marcia. And at the moment, we don't have anything on the books to bring another sample back from an asteroid for NASA. But I will point out that we are collaborating very closely with the Japanese Space Agency on their mission, Hayabusa 2, which is actually bringing a sample back from the asteroid Ryugu in December of this year. And so we've been working really closely with them. Both our OSIRIS-REx team and the Hayabusa 2 teams have been working closely together, and we'll be sharing samples with each other from both of those missions. We're also, of course, partnering with the Japanese Space Agency on a mission to bring a sample back from Phobos, which is one of the 2 moons of Mars, and that mission is set to launch in 2024. And so that'll be a really interesting mission to bring a sample back from another type of small body that we think was potentially an asteroid at one point in time and was captured into Mars's orbit. And then, of course, we're beginning the planning stages to bring a sample back from the surface of Mars at the end of this decade, to bring back a sample that's been collected by the Perseverance rover. So these are all the sample returns that we're currently planning right now, and bringing samples back is a real challenge. It is actually quite challenging to do that, but clearly OSIRIS-REx is doing it, and Hayabusa 2 is doing it, and it can be done. So we look forward to potentially having additional missions like that in the future.
Operator, we do have one question from social media. This one, I think, is for Lori. We are asked, why was the site Nightingale, why was it chosen for the sample collection from Bennu?
That's a great question, Alana. When the OSIRIS-REx spacecraft arrived at Bennu, they were hoping or expecting to find an asteroid that had lots of fine-grained material. They oftentimes talked about, looking for the sandy beach on Bennu. And when they arrived, they found out that it was really a rocky and blocky place that really didn't have any large patches of small, fine-grained materials. And so the team spent a great amount of effort doing reconnaissance over the entire surface of Bennu and trying to find some of the best spots where they could collect a sample, not only based on the science, right? They're looking for the place that might have, Jamie talked about these carbon-rich, potentially organic building block minerals that are present on the surface of Bennu, and they wanted to look for a site that might contain some of those rocks, but they also needed to find a place that would allow the spacecraft to safely descend, collect a sample, and safely depart, and a place that would have rock particles that were small enough, 2 centimeters or smaller, that could be ingested by their sampling head. And so they did a lot of work looking across the whole surface of Bennu, taking into account all those 3 considerations, and Nightingale came out at the top of the list of being a place that had what appears to be sampleable material that's small enough to fit in that can be ingested by the sample collection head, that appears to have high scientific value. And while it's going to be a challenge to get in and out safely, the team have worked very hard to develop a good approach to safely collect that sample tomorrow.
One moment, please. Our next question goes through Leo Enright from Irish Television. You may go ahead.
Thanks very much. A couple of questions. I was a little disappointed.
I think we may have lost Leo on the phone line, so let's go ahead to Keith Cowling from NASA Watch.
These days from NASA about the collection and utilization resources in the solar system. Indeed, the recently signed Artemis Accord specifically deal with this issue regarding the Moon, Mars, asteroids, and comets. Is the OSIRIS-REx sample system open source, the collection system? And can other space agencies or companies use this technology? And is it being considered for use in other missions? And the same question for the Lucy, Psyche, and DART systems. In other words, will this stuff get reused by more and more missions?
That's a great question, Keith. This is Lori, and I would have to go off and get some more information for you on the on whether or not the sample system is open source, and I can certainly find that for you and make that information available. I'll leave it to Hal and Lindy to respond to Lucy and Psyche.
Yeah, I'm happy, Lindy here, happy to respond on behalf of Psyche. One of the aspects of the planning of the Psyche mission that we're really excited and proud of is our partnership with Maxar. This is the first time that Maxar has partnered with NASA for deep space exploration. And one of the many reasons that we selected Maxar as our partner to build the chassis and the solar electric propulsion system for Psyche is that they're incredibly experienced at building systems like this, and over 100 communication satellites in orbit around the Earth. And in fact, it's our hope that the fundamental design of the mission, because we've been able to drive prices down, will make it available for future missions to use. And so that's exactly one of our goals.
Yeah, I could add to that. That's actually an interesting question, right? In general, most of the hardware that's being built for Lucy is proprietary hardware, right? But one of the key aspects to be able to make missions like Lucy affordable is that, and I mentioned this during my talk, right, is to base it on things that have flown before, right? So, for example, our bus is based on Lockheed Martin's history. It's very similar to OSIRIS-REx and Odyssey, if you remember that, in orbit around Mars. Our instruments are also very high heritage, but none of it is actually open source, right? Because it takes so much for these companies to develop these technologies that they keep it proprietary.
Thank you. The next question comes from Michael Grushko. You may go ahead.
Hi, thanks so much. I have a question for mainly Jamie. Could you elaborate on some of the specific sort of science questions that you and your colleagues around the world are going to be examining with the Bennu samples once they're back in the lab? Are there any particular compounds or sort of chirality questions that you all are going to be examining right out of the gate? Thanks.
Yeah, that's a great question, and chirality is exactly what I was going to answer, because that's something that our lab at NASA Goddard focuses on. There's the science team has been busy putting together a lot of different hypotheses to test, and with a variety of tools. But I can tell you a little bit about the amino acid question, which is a type of molecule we're very interested in studying. We know that amino acids are present in carbonaceous meteorites, so we know that they are extraterrestrial molecules. We know that they are essential to life on Earth, and so we're trying to look at that connection of exactly which amino acids may be found on Bennu and which amino acids were present in the solar system, and how they might have been distributed to the early Earth, and how that might have helped life on Earth. Because life on Earth uses only 20 amino acids, but we see many more than those present in meteorites. So we're trying to look at the distribution. We are also looking at chirality, which you mentioned. And just to briefly explain that, amino acids can exist in two mirror image forms that are non-superimposable, like your hands. Abiotic chemistry, so chemistry in the absence of life, tends to produce equal amounts of the two forms. but life on Earth uses primarily the left-handed version of amino acids. And so it's a big question in origin of life research as to why and when and how that happened, why life on Earth uses the left-handed. And there's some clues from meteoritic analyses where we see excesses of that, of those left-handed amino acids in meteorites. We're looking for similar evidence in the Bennu sample. And as I said, because Bennu is collected cleanly, there's going to be much less chance that there will be any contamination from Earth samples for that. So if we can find that type of chiral excess, it will help us understand the what if that excess might have been widespread in the early solar system when life got started. I hope that helps to answer.
Terrific. Thank you.
Okay, next question.
Question comes from Robert Holtz from the Wall Street Journal. Thank you.
Hi, I'd just like to ask a question that is really a follow-up for that excellent question there, and also for Jamie, which is, I wonder if you could just help my readers understand a little better the competing theories of origins here. I mean, on the one hand, there's a great deal of, fundamental chemistry that is aimed at looking at how these amino acids and other organic chemicals necessary for life would have come into being on their own as a result of terrestrial chemistry. And then, of course, as you've just been talking about, there's considerable evidence that these molecules are widespread in the cosmos. So, what are the competing theories of the origins here? Help my readers understand a little bit about, is the chemistry of life just simply so inevitable that it arises everywhere? Or is this some of a more specialized event?
Sure. That's a really great question. And so these types of organic molecules and building blocks that we're looking for, we are finding them forming in many different environments. And so there's scientists studying the early Earth and studying simulations of the early Earth to understand how these types of molecules may have arisen on Earth's surface through hydrothermal events or atmospheric chemistry, for example. But we also know that these types of molecules and this type of organic chemistry occurred in extraterrestrial environments, because we see that evidence, for example, in meteorites. And we know that the early Earth was bombarded with impactors that would have brought these ingredients to the early Earth. So we know there were a lot of different potential sources of these molecules. There's a lot of, what we don't know is the relative importance of these different sources right now. So we don't know which of these sources of organic chemistry were essential for the origin of life on Earth or the potential for life elsewhere. So one of the things that's interesting to do in studying the meteorites is looking for anything that is unique or might have been delivered uniquely by these extraterrestrial sources that we can't find or explain from a terrestrial source, because that might help us understand whether these extraterrestrial sources were essential for the origin of life. And I guess the other thing with them is trying to understand how widespread this chemistry was. These molecules do seem, and this chemistry does seem to be fairly widespread, and so that gives us, it helps us think that maybe these types of building blocks could have been delivered to many different planetary surfaces, not just the Earth. And so what we're looking at really here is those building blocks and looking at their formation and evolution and distribution. And then it's other types of astrobiology research that would take those ingredients and figure out how life got started from those ingredients.
Okay.
Thank you. That was great.
Thank you, Jamie. We're going to jump over to an online question from Jeff Faust. Lori, I'm going to have you take this one, and then Hal, of course, you'll take it. But the question is, what effect has the pandemic had on the development of these missions, particularly those like Lucy with narrow launch windows?
That's a really great question. Of course, the pandemic has impacted everybody in every walk of life across the globe in one way or another. And of course, our missions are no exception. I can tell you that for each of our missions, we've got a variety of different types of impacts. In some cases, some of the facilities that were being used to build and fabricate the equipment were shut down for a few months, and so there were some delays associated with that. And in some cases, we're seeing, even with people coming back to work on the job, that some efficiencies are slowing down. So we're not making quite as much progress in some areas. But what I can tell you is that because DART and Lucy are both set to launch in 2021, they've now risen to our highest priority to get them launched on time next year. Just as we did put a substantial focus on the Mars 2020 launch in July, we put a lot of emphasis on keeping those teams safe and healthy and putting in place measures that help those teams to work effectively and efficiently and while keeping them safe and healthy. And we're now doing the same thing with DART and Lucy to keep them on schedule. And so far, both of those missions are performing on schedule and set and making progress towards their launch dates in July for DART and in October 21 for Lucy. And so both of those are moving forward very well. But Hal may be able to share some other more particular details related to how Lucy's been dealing with pandemic issues.
Yeah, let me just start off by saying we are in remarkably good shape. And, when all this started, I have to admit that I was really frightened, right? But our team has done an amazing job of putting together a safe environment with independent teams that don't cross one another and work. We have one team that, let's say, works Monday and Tuesday for 11 hours, and then the second team that comes in for the rest of the week, and they swap off and never meet to try to keep everybody safe and isolated and keep Lucy moving along. We've reorganized how the hardware is coming together. Again, it was an amazing job by really competent professionals who are agile and flexible and have been able to adjust their schedules accordingly. It couldn't have happened for a worse time for us, right? Because if you think about it, early on in the mission, it's mainly designed and people can work at home. Late in the mission, all the hardware is concentrated in one place, which sort of isolates the mission from the environment. It hit us just as we were about to take delivery of all our hardware, and we had hardware all over the world that needed to get delivered. But people worked it out and got everything where it needed to be, and we are really in good shape.
Thank you, Hal and Lori. Next question.
Next question comes from Neil Patel. You may go ahead.
Hi, my question had to do with autonomy for these upcoming missions. I know that with OSIRIS-REx, there's quite a bit of new kinds of autonomous systems being implemented, especially when it comes to the sample collection maneuver. I'm curious to know if, when it comes to DART and Lucy and Psyche, if there's any sort of specific role that autonomous systems might play when it comes to some of the mission's objectives and goals. Thanks.
So this is Lori, and you make a really good point there that there are a lot of autonomy in all of our planetary science missions, because of course generally we've got light times to deal with, and most activities need to be conducted. If they're rapid action activities, need to be done autonomously. And as you note, OSIRIS-REx for the sample event tomorrow, for the tag event, all has to be done autonomously, and there was a lot of technological innovation put in place to develop and use a new technique that takes advantage of the features on the surface of Bennu to help navigate the spacecraft down. I'd like to see if maybe Andrea would like to talk a little bit about some of the autonomy that's implemented on DART that allows the spacecraft to execute its maneuver when it impacts Dimorphos.
Yeah, so
as it's in the terminal phase right before it's going to impact the smaller asteroid, it'll all be done autonomously. And so the main DART payload consists of an instrument called the Didymos Reconnaissance and Asteroid Camera for optical navigation, and it's called the Draco. And so that's a high-resolution camera that will support the navigation and targeting as DART autonomously navigates towards Dimorphos, and will provide imaging of the moon and impact site for the investigation team. And so DART feeds a system called the SmartNav system, and so all these images will help it autonomously navigate and be able to distinguish between the two bodies and impacting the smaller asteroid it approaches. Lindy, are you able to talk about autonomy for Psyche?
Yeah, absolutely. I think Lori's main points are the key ones for us. We have light time communications lags to deal with, and we're not doing any kind of touchdown activity, but one thing that we are doing to make sure that we maximize our data return is that almost all of our instruments will be on measuring largely autonomously almost the entire time that we're orbiting. And so that's going to be one of the key things about the spacecraft, that the spacecraft as a whole is going to be fine to take measurements in between the times that we communicate with it.
Thank you. Next question.
The next question is from Christina Anderson. You may go ahead.
Hi, AWPS News. So someone took my question earlier, but I would like to know if you're going to use, apparently, I would think you'd be getting a really huge trove of data back on Psyche and the others. And I'm supposing that you must be using AI and machine learning to examine the data and to try to get the most out of it in an organized fashion. Could you talk a little bit about that? Seems like that's the big payoff. So thank you.
I'm happy to start if you'd like. Lindy here with Psyche Mission. Yeah, we are already working on our data pipelines to make sure that we have all of the methodologies that we're using to process the data as it comes back going as smoothly as possible, well ahead of time. And I will add that, of course, there's always human eyes in the loop on the data as it comes out in its final form. But one of the things that we're really committed to is sharing with the whole world absolutely as fast as we can. And we're expecting to be able to put our images out on the internet very, very quickly after we receive them ourselves so that everyone can be looking at the same time. And that's part of the benefit of having a highly automated data processing system.
We have a question from social media. I think this is best suited for Andrea. I've heard that Bennu is a potentially hazardous asteroid and that it might hit Earth one day. Should I be worried? Hi. No. There's no concern to be worried. So Bennu orbits the sun every about 1.2 years and makes relatively close approach to Earth every 6 years. So by current definition, Bennu is a potentially hazardous asteroid whose orbit is predicted to bring it within just 5 million miles or 8 million kilometers of Earth's orbit. Between the years of about 2175 and 2199, the chance that Bennu will impact Earth is only 1 in 2700. But even still, that's why it's important to find, track, and characterize asteroids as early as possible. So it's still a pretty slim chance with 1 in 2700. So I don't think that there's much to worry about with that. Thank you, Andrea. Operator, this will be our last question.
Okay, the last question goes to Michael. I'm sorry, Michael. I'm going to murder your last name. Goretzko? from National Geographic. You may go ahead.
Hi, thanks so much. This is a question for Lori and the panel. And we've been hearing in this discussion about all these wonderful missions, but looking even beyond NASA to the global community, there seems like there's just a surge of missions exploring and visiting these small bodies. I mean, what have been the key factors that have enabled this sort of surge of exploration to these worlds?
It's a really interesting question. I think that again, there are so many of these small bodies out there, and to really understand what they can tell us about early solar system formation, going to require a fairly decent sized sample of going to and visiting multiple types of small bodies and going to different parts of the solar system to look at the different types of small bodies. And I think Hal spoke to that really well at the top of this press briefing about looking at that diversity of those different types of objects can really help put that puzzle together. And certainly the participation of the global community in that effort continues to add and contribute to the overall picture that we're trying to put together. So I don't know if any of the other panelists want to respond to that as well.
Sure. I don't have a lot to add to what Lori just said. These, the small body populations are really our best chance of trying to figure all this out, right? If you look, when I got into this a long time ago, we used to believe the planets sort of formed in the region we now see them. And then really what happened is that it's as if somebody picked up the solar system and shook it real hard, right? And so these objects that are left over have moved a lot and have witnessed a lot. And in order to really put the whole story together requires a big sample, as Lori said.
Thank you so much.
Okay, and that's what we have time for today's News Telecon. Thank you for all the journalists who have dialed in today. I'd also like to thank the panelists and our operator for the time that they gave today. If you joined this telecon late, you can listen to the entire recording by dialing 1-888-566-0569. Again, that number is 1-888-566-0569. Continue the conversation and keep the asteroid science and planetary defense questions coming at hashtag to Bennu and back. Thank you.
That concludes today's conference. Thank you all for participating. You may now disconnect. Speakers, please stand by.